Okay, let's start talking about logarithmic and exponential equations. On some of these, you will have to use your calculator, okay? I'm actually going to start with exponential equations. This is in section 6.6 of John Grimma's stuff. I'm actually skipping the first subsection because we've already done problems like that. Okay, he already sort of did that as a reminder. So let's look at a different type of question here in the following subsection where you're going to need your calculator. I'm actually asking you to answer to 4 decimal places where it's needed, where you don't have an exact answer, okay, rather than just 2 like John Grimm is doing, okay? So let's just keep that in mind as we're going through. In number 14, I've got 2 to the x power is equal to 10, okay? I want to solve for x. Okay, so this is what we're doing here, solving for the unknown in each case. Do you see a way of rewording this question? I could write it this way. X is equal to the logarithm base. What's the base here in this? Is there a base here? Yeah, base 2. What's the value of this exponential? It's supposed to be 10. Okay, logarithms are exponents, right? So an equivalent way of writing this is x is equal to the logarithm base 2 of 10. Now, you remember that we studied the change of base formula here. I'm going to use it this way. We said to use the change of base formula in the case where you've got a base which is neither 10 nor is it e, okay? Neither the common logarithm nor the natural logarithm. You can use the change of base formula here, okay? So use either the common logarithm like I'm doing or the natural logarithm. The logarithm base 2 of 10 would be the logarithm of 10 divided by the logarithm of 2. So here's where we would need our calculators. Again, go ahead and work this out yourself. Make sure you're getting the right answers to these. So you don't want to mess up when it comes to the exam just because you push buttons wrong on your calculator. Okay? And to 4 decimal places, I get this, 3.321. 9. Okay? All right, so that'll be the answer. Now, I could do this. I could just double check on my calculator. I could go 2 to the, actually the previous answer here would be the best way to do it. And I should be getting what? 10. Okay? Now, if I plug this in, if I plug this in for my answer here, actually the 2 sides aren't going to be precisely equal, of course, because this is only rounding. Okay, anyway, let's keep going here. How about the next question, number 16? E to the x is 1.15. Do you see this is equivalent to saying x is the logarithm base e of 1.15? But logarithm to e, we usually write as what? ln, right? So you want to use your calculator for that. Let's go ahead and clear it for the previous one. Okay, so I'm going to be taking the natural logarithm of 1.15. And rounding it, I think I get 0.1398. 0.1398. Okay. Again, I could test that, but I'm not going to be checking my answer in every single case here. Okay. There we go. All right, let's keep going here. So some exponential equations. Okay. Now, this is truly an exponential form like we had right from our original definition. How are you going to solve for x here? Okay, you cannot do this. You can't go 4 times 3 is 12 to the x power. Okay, in order to get 12 to the x power, that you would have to have 4 to the x times 3 to the x. That is indeed 4 times 3 to the x power, which is 12 to the x power. Okay, do you see what I mean? That's not what we have, though. We just got 4, this constant. It's not being raised to the x power here. So don't try to write that as 12 to the x power is 24. You're going to mess up. Okay, that's not right. Well, what I'm going to do is divide on both sides by 4 instead to make this look similar to the equations I've already dealt with. That would imply that 3 to the x power, how many times does 4 go into 24? 6 times. These are equivalent equations. The 3 to the x there has to be 6, is all we're saying. Okay? Now, what would x be? It would be the logarithm base 3 of 6. Okay? And that could be what? Let's use natural logarithms this time. Natural logarithm of 6 divided by the natural logarithm of 3. Okay, using our change of base formula. This time with natural logarithms for no particular reason, just for the sake of variety. So I got natural logarithm of 6 divided by natural logarithm of 3. And let's go ahead and do that. So I get 1.6309. Okay, 1.6309. Okay, now if you have time for the exam, during the exam, you might check your answers just to make sure. How about this one? Okay, this is kind of similar to the previous one. Okay, what am I going to do with the 14? I'm going to divide the 14 out on both sides, isolating the pure power function, right? Okay, the 14s would cancel here, and this would imply that e to the 3x is, how many times does 14 go into 42? I think it's 3 times. Okay? Now I'm going to rewrite this equation, okay, in logarithmic form. You see, if I want an exponent, logarithms are the tools to use, right? If I want an exponent, logarithms are the tools to use, okay? Now, let's rewrite this in exponential form. The exponent, 3 to the x, has to be the logarithm base e of 3, which I really should have written this way, ln of 3. Okay, I occasionally do this just to remind you. I don't know. Okay, so I've got 3x as this. I want x. Right now, natural logarithm of 3, that's just a number, right? What I'm going to do is in my calculator, I'm going to take that and I'm going to divide it by 3 on both sides, and that should give me my x value, right? If 3x is the natural logarithm of 3, x should be 1/3 the natural logarithm of 3. Okay? Now get it right on your calculator here. Let's make that common error here. Natural logarithm of 3 divided by 3. Oh, the answer is 0, right? No. What did I do wrong? Yeah, I forgot my parentheses right after the 3 here, right? That's natural logarithm of 3, and then I want to do that. Divide that by 3. Okay, so I get something reasonable. 0.3662 is what I get for my answer to 4 decimal places. Okay? Alrighty. Alright, looking good here. Let's try a few more. Okay. Now this one's going to be a little bit different here. Okay. Notice that I have an exponential on both sides. Remember when we were working like this problems like this previously, a couple videos ago, we found a convenient common base, and then we worked without even knowing what logarithms were, right? Okay. Well, there's not a convenient common base for 2 and 3. There's no rational number to, say, a whole number exponent that yields both 2 and 3. Okay, so what are we going to do? I'll show you what to do in a case like this, where you have an exponential on each side and bases that just have no relation to each other, you know, as far as exponents go. Choose your favorite logarithm. I'll use ln. I'm going to do ln of each side. Okay? I'm going to take the natural logarithm of each side. Okay? And then I'm going to use now it could have been common logarithm. I'm going to choose one of those because I'm going to need my calculator on this. The answer to this is going to be ugly. Okay, there's not going to be some nice fraction or anything. Now here, I'm going to use this property of logarithms. Remember, if I'm taking the natural logarithm of a power function, I can take the power and put it out front as a multiplier. So that's actually what? X times the natural logarithm of 2. And then bring the power out here, x times natural logarithm of 3. Now what did this person do wrong? Okay, what did I do wrong that you would object to? Yeah, probably, you know, there's an order of precedence in our operations. This should technically be interpreted as x minus 1 times the natural logarithm of 3. 1 times the natural logarithm of 3 is natural logarithm of 3. So this is really x minus the natural logarithm of 3. Is that what we want? No. What did we forget? We forgot parentheses there. Okay? Now don't get excited about what you see right here. Oh, this is so difficult. It's really not. Okay? If you want to, you could do the following. Take your calculator right now and find the natural logarithm of 2 to more than 4 decimal places, and natural logarithm of 3 to more than 4 decimal places, and treat this as an Algebra 1 problem. Remember, this is nothing fancy. This is just what? That's a number, and that's a number. Now, why I said take it to more than 4 decimal places is you're going to be performing some manipulations here, and to be accurate to 4 decimal places, what you should really do is take more than 4 decimal places, perform your manipulations, and then go ahead and round. Okay, I'm going to do something else. I don't want to go through all that. I'm going to remember that natural logarithm of 3 is just a number. I'm going to use the distributive property. Natural logarithm of 3 times x, natural logarithm of 3 times 1. Okay? Alrighty? Now, what I'm going to do here, the natural logarithm of 3 is greater than the natural logarithm of 2. So I think this might be a good thing to do. I'm going to move this guy over to the other side. In other words, technically adding the natural logarithm of 3 to each side. And I'm going to subtract this from both sides. Like that. Why? These two have a common factor now. Okay? Do you see what I can write here? That's really x times the natural logarithm of 3 minus the natural logarithm of 2. Okay? Okay? This means the natural logarithm of 3. Now, you don't have to do this, but I'm going to do it. It's x times the natural logarithm of what? 3 halves. Remember, the difference of the logarithms is the logarithm of the quotient? Okay, if you didn't want to do that, you could have just left this the way it is. In any case, you're going to solve for x by dividing on both sides by this. So this is the natural logarithm of 3 divided by the natural logarithm of 3 halves. Okay, so let's go ahead and use our calculator on that and see what we got here. Again, you could have used common logarithms instead. And I get something like this. You might, this one's complicated enough, you might actually want to go through and double check your answer, but this is what I got. 2.7095 about, okay, to 4 decimal places. Okay. Alrighty. All right, that's clear then. All right. Let's see. One comment I wanted to make right here. When I write this right here, I went x times the natural logarithm of 2. The natural logarithm of 2 is a number. Usually we write numbers before the variable, right, or the unknown. We write 7x, not x7. We choose to do it this way, however, this time, because if you go like this, how would that be interpreted? That looks like the natural logarithm of 2x, right? Which is completely different than what? X times the natural logarithm of 2. So if you, to avoid this situation, which is what you don't want, you would have to use parentheses like that. So you're saying the number natural logarithm of 2 of x times 2 times the x. Okay? Let me focus this for a second. Sorry. Okay? All right. This is actually a shorter way of doing it. I save a little ink that way. Okay? Anyways, how about this one then? Okay? All right. Now, if you guys look at the form of the answer on this one, there is a way we could have gotten away without taking natural logarithms of both sides. And we could actually do that on this one as well. Okay? But I'm going to go ahead and not do that. Now, I might mention how to do it that way in a minute. I'm going to use common logarithms this time for no particular reason. Okay? And then this would be what? Take the x out. Take the x minus 3 out with parentheses. These are numbers. Not going to get excited about it. This is actually baby algebra now with fancy looking numbers. Okay, use the distributive property. I'll move this guy over to this side. Make it look a little bit better. Move this guy to the other side. So subtracting x log 2 on each side. See the common factor here? Is x times what? Log 6 minus log 2? What would that be? Log 6 over 2, which is also known as what? Log 3. Okay? And I could write x this way, dividing on each side. 3 log 6 divided by log 3. And then let's use our calculators. Okay? Okay? Now it's really good for you guys to go through and punch the numbers in, just like I'm doing here. Okay, get used to using your calculator. 8, 9, 2, 8. Okay. Alrighty. Alright, just to mention the other method that I was talking about here. See, I've got 2 to the x and 6 to the x. I could have thought about that this way. 2 to the x equals 6 to the x times 6 to the negative 3 power. Okay. Then I could move this over to the other side. That'd be multiplying by 6 to the third on each side and dividing on both sides by this. And this would give you your 3 to the x. And then go ahead and work out, take logarithms base 3 of both sides. Okay, that would be another way of working it. Alrighty? Alrighty, you'll end up with the same answer. Alright, let's look at some other types of questions here. These are logarithmic equations. Notice we don't have things written in terms of exponentials. Now it's log base 2 of x is equal to 3. Now do you remember the what? The domain of any logarithmic function is what? All positive real numbers, okay? So if you get any answers that are 0 or negative, you got to kick those out as superfluous, okay? Extraneous, some people like to say. Here's another thing. Do you remember this? B to the logarithm base b of x is equal to x. We will use that little principle throughout. We said this could actually be considered a definition of the logarithm base b of x, okay? Okay, x has to be greater than 0. Okay, anyway, back to it. Now, b here is 2, right? So if I go 2 to the logarithm base 2 of x equals 2 to the third, so these exponents are equal, right? This would just boil down to 2, or to x, which is 2 cubed, which is what? 8. Okay? Of course, if you were really on the ball, you would have seen what? That this is equivalent to that anyways. We practiced that earlier. Okay? We practiced that somewhat earlier here. Now let's go ahead and try this one here. How would you write this? In fact, let's go ahead and do it that way. Can you rewrite this as an exponential equation anyway? What's the base? X, right? What's the power? Well, the whole thing is the exponent, so that's got to be, we know its value is 5. Well, that's equal to 32. And then what you can do is take the 5th root of 32. Okay? Do you know how to do that on your calculator, by the way? That's 32 up caret 1/5. Okay? This we could actually do in our heads. If you guys know what the 5th root of 32 is, it's actually 2. Okay? Alrighty. Well, these are not so bad so far. Okay, we haven't even needed our calculator. Okay? All right, let's come back here. Can you rewrite this one? Maybe if you want to stop here on some of these. Can you rewrite this one in terms of exponential functions instead of logarithmic. Sometimes easier. What is this? It would mean the x minus 5 is the base to the power 2. That would mean x minus 5 is 9, x is 14. It's by adding 5 on each side. What do you think? Okay, pretty easy? Okay, these ones are pretty easy. Okay, they're not necessarily going to stay easy, though. Now, here's something you could do. Notice I have logarithm base e on both sides because it's natural logarithm. You could use this principle that I have up here and let b be e and get rid of both these natural logarithms. But an easier way to think of this is, do you remember a logarithmic function to a fixed base is what? 1 to 1? Okay, logarithmic functions to a fixed base, like b, is 1 to 1. Okay, so if you graph that, it would pass the horizontal line test. And of course the vertical line test because it's a function. But anyway, how can these two be equal then? The only way these two can be equal if it's a 1-to-1 function is if the two input values are equal. So those have to be equal. Well, that's a baby equation, isn't it? Okay, let's add 10 on each side and we would get what over here? 6. Subtract x on each side and we would get 6 is equal to x, or maybe rather like, instead of brown is the hat is brown, okay? All right, x is 6. People, and some of these more advanced ones, double check and just make sure none of the, it's not going to happen on this one, but you want to make sure when you, just as a quick mental back substitution, it isn't a full check on the problem, but back substitute, make sure you're not taking any logarithms of negative numbers, okay? Well, I'm going to illustrate that in another problem here, where it can be a danger here. Sometimes you can get an extraneous solution in some of these, so just be a little bit careful about that. Make sure when you back substitute the value you supposed in the expression that everything makes sense, okay? Don't be taking logarithms of anything except positive real numbers. All right, how about this fellow? Okay, you notice we have a common base here. Common base is what? 3, okay? So we can combine these this way. Can't I write that as a single logarithm then? Logarithm of the quotient. The difference of logarithms is the logarithm of the quotient of the values on the inside. They're the input values, right? So this becomes this, okay? Now, can you rewrite this? I can go 3 to this side is 3 to this side, right? Or just think about rewriting this, what this expression would say. It's 3 to the minus 1 power. What is 3 to the minus 1 power? It's a third, right? Now, when I see an equation like this, I imagine multiplying on both sides by the product of the two denominators. In essence, and then when you cancel, in essence, that gives you the idea of cross multiplication. Do you remember that? So the 3 times the x, 3x, has to be what? 1 times the x plus 6, which is x plus 6. Okay, subtract x on each side. We would have 2x's is 6. X must be 3. Quick double check here. Let's come back. If I let x equal 3 in either one of these, would I be taking a logarithm of a negative number or 0? I would not, so we're cool. Okay, looks good. All right, let's go on. Let's go ahead and take a look at this one. What would you do with this? Can you combine these logarithms? Well, they have a common base here, so you can. What happens if you add logarithms to the same base? You get the logarithm of the product of the two inputs, okay? So this becomes this, right? Okay, now we're going to come over here. Can you rewrite that? This would be what? 2 to the third, right? Okay, 2 to the third. Okay, this would end up being what? This implies I'm running out of real estate here. X squared plus 2x equals 2 cubed is 8, right? And I'm going to come back over here and go x squared plus 2x minus 8 is equal to 0. This is a quadratic equation. We want to put it in standard form. Okay, Can you solve that? Can you think of how to solve that? Usually when you've got a quadratic equation, you want to try to see if you can't factor it first, right? So let's go x plus 4 times x minus 2. Doesn't that work? Okay. I think that works for us. What would the solutions be just to this equation? X equals negative 4 or 2. Now, do both these work back in the original? The answer is no. This is an example of this. I can't let x equal negative 4 in here. I'll be taking a logarithm of a negative number. There is no such thing. Well, there actually is something when you get such a thing when you get into higher mathematics, but it ends up being complex value. Okay, well beyond the purview of this course. It's also, I mean, that's enough. That kills it. So that's out. Okay, so x equals 2. Does that work? Yes. Go back and take a look at it. That one works. We got to kill off this one. That doesn't work. Okay, let me do one last one here where the answers are not so neat. He's given you questions where the answers are all really neat, which is fine. But let's go ahead and do this. What's the base here? It's logarithm base 10, isn't it? Okay, because there is no subscript. Okay, maybe you want this in there. I don't know. Combine these two. This would be logarithm base 10 of x times x minus 2 is equal to 1. Okay, so let me put the base in there just for convenience. This would mean x times x minus 2 is 10 to the first power. That would mean x squared minus 2x equals 10. X squared minus 2x minus 10 is equal to 0. Okay, let's see if there's any solutions here. Okay, you try factoring this. It's not going to work. What are you going to do? Resort to the quadratic formula. Negative b. Okay, so b is negative 2, so negative b would be positive 2, plus or minus the square root of b squared. B is negative 2, so if I square that, I get positive 4. Minus 4, a is 1, c is negative 10, all divided by 2 times 1. That's our 2a. And you see that's 2 plus or minus the square root of, it looks like 44 over 2. Okay, so x is 1 or 2 plus or minus. You see the square root of 4? I could factor out. The square root of 4 is 2. And then, canceling my 2 in both places, x is 1 plus or minus the square root of 11, isn't it? Okay, now are both of these going to work? The answer is no. What happens when I go 1 minus the square root of 11? I get a negative number in here and also in here, but either one. Just one's enough to kill it. So the only actual solution is 1 plus the square root of 11. When I plug that number in, neither of these are going to become a negative number. In fact, they're going to, or 0, they're going to become positive. And this should actually work. If you don't believe it, you can, of course, give that a try. Alrighty? Alrighty. Now, let me address one last question. We talked about it in a previous video. Suppose logarithm base b of a is 1/4. I asked you what the logarithm base a of b would be. Okay? Well, think of it this way. The logarithm base b of a, all right, that's 1/4. You can think of that as, say, the natural logarithm of a divided by the natural logarithm of b. Okay? If I asked you to reverse these, what would that be? That would be the natural logarithm of b divided by the natural logarithm of a, using the change of base formulas. Okay? Okay, there's other ways to think about this, but this is maybe an easy way that you're familiar with. It comes right off what we just learned. What's the relationship between these two? All I did was, the logarithm base b of a is 1/4. The logarithm base a of b is what? It's reciprocal, which is 4 over 1, better known as 4. So there's the answer to that mysterious question. Okay? Alrighty, that should do you for now.